Welcome guys. In today's tutorial, we'll be looking at drawing the shear force and bending moment diagram for a simply supported beam. And we'll be using the example as shown on the screen. So with this example, we have a 20 kilonewton point load acting at C, which is 4.5 meters away from the hinge support at A. And then on the right support, we have a roller support. Right. So let's begin. In order for this structure to be stable, we'd have to consider three equilibrium equations. So we'd have to consider the summation of all downward and then upward forces. So summation of vertical forces must be zero. Again, we'd have to consider summation of all horizontal forces. And then finally, we'll consider the moments about the supports also being zero. So we'll consider three equilibrium equations. A summation of Fy must be zero. B summation of horizontal forces must be zero. C and then that will be finally summation of our moments must also be zero. Right, so that will be the first thing. We've been able to establish the three equilibrium equations we'll be using. When we consider our structure, we don't have any horizontal force or reaction. So condition B will be out. We'll be focusing on condition A and then condition C. Right. So the next thing we are going to do is to establish our sign convention. So sign conventions. So in our tutorial, we would consider all upward forces as positive and all downward forces as negative. Right, again, we'll consider all clockwise moments as positive and all anti-clockwise moments as negative. Right, so let's begin. So we will start off with the first condition. So let me call that 1. So summation of our Fy equals 0. Now, when we look at the sketch or the example at support A, which is a hinge support, we'll have a vertical reaction. And let's call that vertical reaction VA. And then at support B, which is a roller support, we'll have a vertical reaction. And let's call that VB. And then at C, we have a point load with magnitude 20 kilonewton. Right. So what the first condition is saying is when you sum this the vertical reaction at A, so VA plus VB, it should be equal to 20 kilonewton. And in that case, that means the structure is stable vertically, or all the vertical forces are in a state of equilibrium. And then again, the moment at A and B must also be equal to 0. So we have a downwards force 20 kilonewton, which is acting at C. And from our sign conventions, we are saying all downward forces are negative. So we'll have a minus 20 kilonewton, right? And then at VA, we also have a reaction, and that is an upward force, so plus VA. And then at B, we also have a vertical reaction, which is upwards, so positive. And all this must be equal to 0. So this will give us VA plus VB equals 20. Okay. And then secondly, we'll consider summation of moment. So 2. Summation of moment. Let's take our moment about A. So summation of moment about A equals 0. So with that, we would have, since we are considering the moment at A, we will not have any moment, that obviously the moment at A will be 0. So we'll have this VB having an anti-clockwise moment about A, and then the 20 kilonewton point load having a clockwise moment about A. So let's just consider the point load first. Now, if we fix A and we release the moment here, we'll realize this 20 kilonewton force is pushing this beam downward. So this beam will be moving this way. So this is a clockwise moment, right? And from our sign conventions, we are saying clockwise moments, we are using positive. So this will be, so the force, which is 20 kilonewton, right, multiplied by the lever arm, which is 4.5 meters from support A, 4.5. And then we'll consider VB. Moment is trying to push the beam upwards. So we'll have an anti-clockwise moment. So that will be minus VB times its lever arm, which is the summation of this, the 5.5 meters and the 4.5 meters. So when we sum them, if we sum that up, we'll have 10 meters. So 10 equals 0. So solving this, we'll have VB equals to 20 times 4.5 divided by 10. And that will give us 9 kilonewton. Right. So once we have the value of our VB, we can slot it into this equation and have, so the first equation was VA plus VB was 20. So that means our VA is 20 minus 9, and that will give us 11 kilonewton. Right, so this implies that at VA we have a vertical reaction with magnitude 11 kilonewton, and then at VB we have 9 kilonewton. If we sum VA and VB, we'll have 20, and the downward force at this C, at point C, is also 20. So if we subtract them, we'll have 0. So that's what we mean by, this, the first equation. Right. Okay, so now move on and draw the shear force and bending moment diagram. But before that, so let's call this 3. Before that, we need to calculate the shear forces at the supports. So let me copy this downwards for clarity. Okay, so draw shear force diagram. Okay, but before we draw the shear force diagram, we need to calculate the shear forces at the supports, and then if we have any load acting on the beam, we'd have to consider the shear forces at those positions where we have the loads. So in this case, we'll consider the shear force at the support A, right? And then from A, we don't have any loading on the beam till we get to point C. So again, we'll consider the shear force at point C, and then from the right of point of the 20 kilonewton point load, we don't have any load again. So we'll consider the shear force at the support B, which is 9 kilonewton. Right, so our first calculation will be, so shear force at A, and that will be equal to, so at A we have a vertical reaction of 11 kilonewton, and we don't have any vertical reaction at A again. So that will give us the only upward reaction here, which is 11. And from our sign convention, we are saying upward forces are positive, so we'll have 11 kilonewton being the shear force at A. And then at B, so shear force at B will be equal to, so, and B shear force at C. So that will be, so when we consider, we've established that the shear force at A is 11 and we don't have any load on the member till we get to C. The resultant shear force at C will be this 11 kilonewton, right? And then this 20 kilonewton, and since it's a downward force, so we'll have minus 20, and that will give us minus 9 kilonewton, right? So that's the shear force at point C. Now, from the right of point C, or the point load at C, we don't have any load till we get to the support, the roller support, and at that side we have a vertical reaction with magnitude 9 kilonewton. So we'd have to consider the shear force at B. So shear force at B will be equal to, so the resultant shear force, remember we have a 9 kilonewton force from this point C. So when it gets to B, the resultant shear force will be this 9 kilonewton, and then this vertical reaction at B. And since it's an upward force, it's going to be positive, so plus 9, and that will give us 0. So shear force at B will be 0. Right. I will move ahead and draw the shear force diagram. To do that, let us draw a line. So we'll try and make the line should be proportional to the example, right? Okay, and then let's draw another line here. And then at C, we also have, let's draw another arbitrary line. So, and then at B, let's draw another line. Let's label, so this is A, this is our C, and that is B. Right. So at A, we calculated the shear force to be 11 kilonewton. So that means we'll be moving up by 11. So this will be 11 plus 11. And then so from the right of the support, we don't have any load till we get to point C where we have the 20 kilonewton. So this shear force will remain constant. So till we get to C. Now at C we have a 20 kilonewton force and we calculated the shear force to be minus 9. So we would have to go down below this line because this line is at 0. So we'll come down minus 9, minus 9 kilonewton. And then from there, the shear force remains constant till we get to B. Then the shear force at B, we calculated it to be 0. Right, so this way. Right, and this will also be minus 9, and this will be 0. This will be 11 plus 11. Right. Okay, so that will be our shear force diagram. So this is positive and this is negative. So that will be our shear force diagram. Now let us go ahead and calculate. So then draw the bending moment diagram. So let us call this shear force diagram. Now, so we move on to the bending moment diagram. So draw bending moment diagram. Right. But before that, I would have to calculate the bending moment, right? So let's say A, maximum bending moment. And that will that will give us the area of the shear force will give us the bending moment, the maximum bending moment. So if we consider the bending moment here, it has a magnitude of 11 and the distance point C is 4.5. We need to find the area of this rectangle, and that will give us 11 multiplied by the 4.5, and that will give us 49.5 kilonewton. We could have also used this part as in the right side, and in that case the magnitude is 9 and the distance is 5.5. We arrive at the same value, which is 49.5 kilonewton. Right, so that means the maximum bending moment is 49.5 kilonewton. So let us go ahead and draw the bending moment diagram. So again, we'll draw arbitrary lines. So we'll try and make it as the same as the previous line. So we can bring it down here, and then we have another imaginary we have another line at C and then finally at B. Right. So we had so this is kilonewton meter. Kilonewton because it's a moment. So right. So our maximum moment was 49.5. If we label this axis right, we'll have so the magnitude is 49.5 and then the distance is what 5.5. So at this point here and then correlating it to the vertical axis here, it will be somewhere here, right? So we'll have it this way at this point here. Then we draw a line and then we draw another line to that point. So that will be a bending moment diagram, and this will be positive. So this is a bending moment. So the value here is 49.5 kilonewton meter. Right. Right, guys. Thanks for tuning in. If you like this video, kindly hit the like button, and if you haven't subscribed, please do. Thank you.